Yeah, thanks for having me. My name is Guannan, and I'm going to talk about our work on reconstructing a continuation passing style semantics for WebAssembly. And this is also the talk we gave at the WebAssembly workshop last month at Popo. But hopefully this time we can make something a bit more clear. And this is a joint work with Alex, Dinghong, and Jiatai. So as we all know, WebAssembly is a stack-based low-level intermediate representation for the web. It is pretty fast and compact, and now has been supported by all those major browsers. And one of the really nice things that WebAssembly has is it offers official formalized semantics from the very beginning. And the official semantics has a dynamic semantics in the form of a small step reduction semantics. It also has a static type system that guarantees or constrain the shape of the stack. And there are also meta-theory results to provide soundness, safety, and control flow integrity, etc. There are also a lot of ongoing work built on top of this formalized semantics, for example, effect handlers or garbage collection, and many others. Let's take a look at how it works for the basic idea of the reduction semantics. And the reduction semantics specify the transition between configurations. And each configuration is basically a global store, as here, a list of values for those local variables, and a list of instructions, E. And we can specify how they change. And one of the examples here is this loop instruction. And notably, this to specify the execution of loop, the standard reduction semantics use administrative instructions to represent evaluation context. And when we have a loop instruction, we will put the loop body into a list label instruction, which is sort of administrative, and we reduce the loop body. First, we have the 1 plus 2 becomes 3, and then 3 plus 4 becomes 7. And at the branching point, we need to look at the label instruction on the stack to decide which point we need to branch, to jump to that. And then we found, okay, we need to expand the loop body again and reduce to the next configuration. So this is pretty much like a standard approach using the small step reductions. And it's also straightforward to translate to an implementation of interpreters. But there are also something that is not good enough for other purpose. And the first thing is that the use of these administrative instructions sometimes can be expensive and very verbose. And because we're using those labels or administrative instructions on the stack, and when we need to branch, we need to search on the stack to find the right label or the right instruction to execute next. And this can be very expensive if we have deeply nested frames or labels. And as we can see from the loop instruction, we also need to have some duplication of those syntactic construct stored in those administrative instructions. Another thing of this style of reduction semantics is that it is not compositional. And by compositional, what I mean is we can obtain the meaning of a larger program by composing the meaning of its smaller programs that syntactically subprograms of these larger programs. And this is a nice property and sometimes can make it easier for program reasoning and program transformation, which I hope I will show some examples later to convince you that it makes some job easier. So in this rest of this talk, I will talk about an alternative to the reduction semantics. And the idea is rather than using a first order representation for those control structures, like those label instructions, and we can use continuation functions in the meta language to represent the control semantics. And the result is a compositional and tail-recursive semantics for a core WebAssembly programs in continuation passing style. And this style of semantics, we can directly implement it as a big step interpreter, or we can also view this as a transformation from WebAssembly to lambda calculus with some addition of functional data structures. Okay, so let's briefly go through the subset of WebAssembly we're dealing with. So we have just standard labels, identifiers, they're just numbers here. And we have value types are also just numbers. And function types take a list of value types to another list of value types. And for instructions, the first group here are really just some simple instruction to manipulate the stack we have non-op, we have the const instruction, and some arithmetic instructions. We also have instructions to manipulate those local variables. We can set the value or get the value from the local variables. And next, we have a set of structured control flow instructions, namely the block instruction, loop, and conditionals. And lastly, we have several control flow transfer instructions to take a branch or to take a jump or to take a function call or return from a function call. And the function body, a function is has identifier x, its function type, the type of local variables, as well as the body which is just a list of instructions. And we just simplify the module to be just a sequence of functions. Okay. And our goal is really to define such a semantic function, which is this brackets, and this brackets maps a list of instructions to another function. And this another function further takes several arguments, which is a stack, environment, and a continuation. And it returns some answer type, which at this moment, we just want to leave it as abstract, since the interpreter can be somehow tailored to different purpose, which you can instantiate this answer type with other concrete types. And to represent values, we just use integers. And the stack is a list of value, and the environment, which stores the value of those local variables, which are also a list of values, or we can think of it as array of values too. And the continuation here is a function, takes a recent stack and the environment that returns an answer type. So far, this is really just a standard CPS interpreter. This is well-known technique, basically from the 70s. But for WebAssembly, as I will talk about later, we need an additional component, which is this trail component in the semantic function. And this trail is really just a list of continuations, or we're basically using this thing mostly as a stack of continuation. And later I will explain how can we provide the continuation and the trail when defining the semantics for those control flow instructions. So let's look at those possible cases for those list of instructions. And the first obvious case is that a list is empty. So here we just have the new, which is empty list, and several arguments here. The sigma for the stack, the rho for the environment, kappa for the continuation, and theta for the trail. And because we don't really have anything to execute in this case, the obvious way to define the semantics is to just, I'm going to call the kappa continuation, providing the current stack and the environment. That's sort of obvious, okay? And next group, we have several instructions to manipulate the stack. And the no-op instruction is really we're doing nothing for the stack, which is to recursively call the semantic function on the rest of the instructions, right? And for the const instruction, we have a number C. We just push the number C on top of the stack, and then recursively call the semantic brackets on the rest of instructions with this newly constructed stack. And for addition, we inspect the input stack and take the top two values from the stack, and then we push the addition of those values onto the stack, then recursively call the semantic function to the rest. Okay. Then for local variables, it's similar, but we're mostly just using this rho, which is in environment, and we can get the value for this variable and push it onto the top of the stack, or we can update the value of this rho by pointing it, the variable x, to the value v from the stack. Okay. Now we need to look at something for the block and branching. And it's sort of not obvious because they're not really manipulating the stack or environment. And before giving the semantics here, let's look at how informally those blocks or branch instruction work. So the first thing to note is that those blocks, they are structured and they can be nested. For example, here I have two blocks and one is nested in another. And those blocks, they introduce a label. They can either be named or nameless as a de Bruijn indices, and those two forms, they can convert it back and forth without losing any semantics difference. Okay. And those labels, they serve as a branch target where we can refer those labels using the BR instruction. And for example, here in the inner block, we have BR label 2 and BR L1. And when we are branching to the target of the block, we're really jumping to the next instruction right after the block. Okay, so which means for BRL2, we're jumping to the instruction after L2. And for jumping BRL1, we're jumping back to the instruction right to the L1. So the idea is when entering the block L1, we need to remember the escaping continuation, which is the instruction after the block. And this escaping continuation will be used for those BR instructions within this block. Okay, that's really the idea we have here. So when giving the formal semantics here, we have this BR block instruction. There are some additional information I will briefly explain here, where we have the block type from TM to TN. And there are also some additional stack manipulation to make sure the resulting stack really takes the right argument. But the key point here is we are constructing a new continuation kappa 1, which is a function. The function takes a new stack and the new environment. And the function body recursively call the semantic brackets on the rest of the instruction, which are those instructions right after the block. Okay, so we're basically defining this escaping continuation as kappa 1. And notably, this kappa 1 is shared as ordinary continuation and also as escaping continuation here. And we're using this kappa 1 in two different places. In the first one, we're using the so-called ordinary continuation, which is a continuation will be invoked when the block just falls through to this one. We're also pushing this kappa 1 on top of the trail. And recall that the BR instruction takes a number, and this number refers to some block target. And consider if this L label is just 0, then here we're when defining the BR instruction semantics, we're just looking at the top element, the top continuation of the trail. So we're getting that continuation by accessing theta and then invoking this continuation. So this is the way we push the escaping continuation following the lexical structure and also accessing that within the lexical structure using the BR instruction. Okay. Then next, let's look at loops. And similar to blocks, those loops, they also introduce a label as jump target. But different from blocks, jumping to those loops will go back to the beginning of the loop instead of going to the instruction right after the loop. Okay. And if within the loop body, if there's no branching happens, the loop just finished. So the idea here is we need to remember two different kinds of continuation for the loop. One is that we really want to going back to the beginning and perform the next iteration of a loop. And the other continuation is the loop is finished. Then we need to go to the next instruction syntactically after the loop. Okay. So with that idea, now we are defining two different continuations, kappa 1 and kappa 2. And kappa 1 is really similar to the way we define for block. It's a continuation for the rest instruction. And for kappa 2, is both the continuation and also the loop entrance, right? So that's the loop body ES here. And note that this kappa 2 continuation is defined as a recursive function. So when we are calling the semantic brackets on ES2, on ES, the loop body, we're also pushing the continuation itself on top of the trail, okay? So that when we have the BR instruction within the loop, it will get to the access to this kappa 2 continuation, okay? The next thing is about function call and return. And for function call, we have use an additional auxiliary function to get the function body by looking up the function. So we get the function body ES here, and we have some auxiliary function to build the initial environment for the function. And the function also has a continuation, which is the instruction right after the function call. That is this rest instruction after the function call. So we prepare a new continuation kappa 1. And when we are going into the body of ES, we're using this kappa 1 as a continuation. So that's when we return. This is where we come back. But we are also using a different trail. We're using a singleton trail that only contains this kappa 1. So this is because those continuations on the trail are really just local to a function. So when we're going into a new function, we can discard the current trail continuations there, right? And then the semantics for return is really simple because we always know that the last continuation on the trail is the one to return. Then we can just access the theta last and invoke it to return, which comes back to the rest instruction after the call. Okay. So now I have demonstrated this core CPS semantics, which is a function taking a list of instructions and returns another function. And this another function makes use of continuation and the list of continuation. And this trail nicely gives semantics for block, for loop, for BR, function call, and return. And this style of semantics is compositional and tail-recursive. So what are they really good for? And I will demonstrate several use cases for this style of semantics. One is to specify new extensions in the language, and we can also support equational reasoning, or we can use this semantics to implement an interpreter to run Wasm programs. And there are also possibly ways to build partial evaluation on top of this interpreter, which is a current future work for this. So for the extensions, we have looked at several extensions. Some of them, most of them, they are about the control flow structures. We have the loops, tail calls, exceptions, and resumable exceptions, as well as we're working on Wasm FX style effect handlers. I will mostly just talk about tail calls and resumable exceptions in this talk. So for tail calls, this is extension that already a working proposal for WebAssembly. And we're mostly taking the same syntax here, this return call instruction. And the way using that, we can explicitly enable tail call optimizations. And the way the tail call works is that suppose we have a function f, and in function f, we have function call to g, and function g has a return call to h. And because the call to h is a return call or tail call, and when h returns, it will not return back to the call where we made for h, but instead we're going back to the caller of g, because suppose this return call is really the tail call. We can also think of this return call is really to perform the return first and then perform the function call. Okay. With this idea, we can define the semantics pretty straightforwardly, just building on top of the existing semantics for call. And similarly, we get the function body ES here, and we build a new environment. But we don't need to construct a new continuation here because we know this is a tail call. We're not coming back to the rest instructions, but instead, we're directly going to return to whatever the current function is going to be returned to. That is the theta last continuation we already have access to. So in this way, we can just discard the current frame and context. And you may also recall that at the beginning of the talk, I mentioned this style of the semantics we proposed here is compositional, and it can make it easier to reason about some of the property of the program. And here we can justify the semantics I just showed for return call by calculating it from the semantics of return and call separately. And now let's pretend we have a function call. It's really made at the tail position syntactically, which means we have the function call here, and right after that, we just put a return instruction. So this is really syntactically enforced. This is a tail call. And because our semantics is compositional, and we can just look at the head instruction and directly apply the semantic brackets, and replacing what we define on the right-hand side of semantics into here. So we're basically unfold the function call, the semantics for call, and we're kind of copying whatever we defined for function call here and preserving the rest of the syntactic structure that is return and rest here, right? This is the same. And we can do the same thing here for the return instruction, basically to replace this return to directly calling the theta last argument here, okay? And the next step is that by the guarantee of the static type system, we can also show that some of the stack manipulation, they're really idempotent. Then we can show this kappa 1, which is really kind of like an eta expansion of the theta last continuation, which means we can directly replace the continuation kappa 1 to the theta last continuation. Okay, so now here, if we look at the definition we gave here, it's really exactly the same definition I have showed at the beginning for the return call. Then we can basically show their equivalence, or they're really just the same thing. And there are other different ways or different uses of this style of equational reasoning that we can calculate the meaning of the programs. Okay, and the next extension I want to talk about is this is a hypothetic extension of resumable exceptions, or we can really see it as effect handlers with unlabeled single operation. So here we extend the instruction set to have this try-catch block, and ES1 and ES2 are both just a list of instructions. And we have two additional instructions, throw and resume. And to give an example here, we can see we have this try-catch block, and inside of the try block, we have a throw instruction. And the throw instruction will transfer to execution to the catch block. And we'll also put two values on top of the stack. One is the error value, another one is a resumption. So the resumption is really a function or a continuation that has been reified as a proper value on the stack. And inside of this catch block, let's first to consume this error value, just print it. And then we can use the resume instruction to invoke the value, the resumption continuation on top of the stack. Then we will go back to the point and continue the execution after the throw. And when the try block finished, the control is then transferred back to the way where we performed the resumption previously. So this is a quite general proposal for the effect handlers. We don't really have other constraint or as Wasm effects has here. But again, this is a hypothetic extension. But now let's look at how can we express this behavior. And the idea is we need to somehow extend our semantic domains, where the continuations are extended with a meta continuation. And here the meta continuation is really a simple function taking the stack and environment. But continuation additionally take its own continuation, namely the meta continuation. So this is not a new idea, but already well explored in the 90s to give semantics for delimited control operators. But here we just adopt the idea to this setting. And we also define the type of handler values, which are a function taking the continuation and meta continuation too. And we need to additionally enrich the value domain to contain those resumptions. Okay. And this figure shows the full definition we have for those try-catch block, the throw instruction, and resume instruction. And the basic idea here, I'm not going to give the full detail here, but just explain the idea. The basic idea is we define a meta continuation M1 here to kind of delay the execution of the rest, which is the instruction after the try-catch block. And then we define a handler, which is the theta 1. The theta 1 is a handler for calling into ES2, which is a catch block. And when we perform the throw instruction, we prepare the resumption, which is this R value here, and the R value here takes the semantics for the rest instruction. And we put the value R here on top of the stack when invoking the handler gamma here. So gamma takes a stack which only has two elements and also the current meta continuation and also an initial empty continuation to delimit the context. And resumption sort of similar, but we are putting the rest instruction into a meta continuation. And then we resume the resumption value on top of the stack, which is the value R here. Okay. We also have an ongoing work to define the semantics for Wasm effects in the same style as in continuation passing style. We already have a working implementation to like an interpreter to run Wasm effects programs, which uses kind of combination of deep and shallow handlers. And the idea is a bit different from the meta continuation, where we use another trail of continuations, which allows us to more flexibly manipulate the kind of fragments of continuation. And the formalization for this CPS semantics is still ongoing work. And another ongoing work we have is the implementation, work on the implementation, and also validate against the official Wasm test suite. Okay. And there are several future work we are interested in. One thing is we want to apply some staging or partial evaluation on top of the interpreter we have built with. And this would allow us to turn the interpreter into a code generator, which potentially can be used as a compiler or program optimizer. And another thing is about establishing the correctness or correspondence of the CPS semantics with the official small step reduction semantics. And there are already well-known work that builds functional correspondence between different style semantics known by Oliver Downby, and they're connecting big step semantics, CPS semantics, and small step semantics. So we're interested in looking at this direction to see if we can also interderive those different semantics. This could be also interesting to make use of the recent SpecTech work and to see if we can derive different style semantics from a single source of truth. And of course, another possible way is to mechanize the CPS semantics in a theorem prover and to show the correspondence or some equivalence compared with the reduction semantics. Okay. So to summarize, I have talked about alternative CPS semantics for WebAssembly, and the key takeaway is we can use a stack of continuation to give semantics for those control flow instructions, blocks, loops, branching, function call, and return. And the CPS semantics is compositional and tail-recursive. And we have already implemented this semantics as a big step interpreter, but you can also view it as a CPS transformer if it could be useful in other cases. And there are several possible extensions we can build on top of that, such as the tail call instructions or resumable exceptions. We do also have implementation here on GitHub, which you can access. We also have a full paper that contains all the technical details, which will be appeared in the proceedings of Trends in Functional Programming this year. This will be the end of my talk. I'm happy to take questions or have discussions about it.
Andreas has a question.
Yeah, hi. Thanks for the talk. Very cute stuff. I like it. We already kind of chatted a little bit about this. So I just want to comment on one thing I just noticed, which I hadn't noticed before. And that is the fact that you can prove that a call followed by return is actually equivalent to return call. So in the actual semantics, the official semantics, that is not the case. And it's very intentionally not the case because WebAssembly actually requires that a regular call grows the stack. And there's even a test that it will eventually run out of stack space so that this will require linear resources, right? So this is actually an example where probably the semantics you have defined has kind of like over beautified it in some and you
Yeah.
probably would need to add some kind of like cost dimension or like somehow remembering how many outstanding calls there are to like accurately model this part of the specification, which
Right.
I don't know, you can argue about whether that was a good idea in the first place, but that's what it is right now.
I see. I see. There are definitely, we're not fully model area specs from the reduction semantics. Yeah, but I agree with you. There are different trades-off.
Yeah. Okay, cool. Thanks.
Thanks.
Hi.
Hi, Sam.
I think I also saw your talk previously.
Yeah. Yeah.
It's very nice. A couple of thoughts. Well, one on Andreas's point, I'm sure you could find ways of augmenting your semantics to be able to keep track of the differences between tail calls and normal calls if you wanted to. One maybe pedantic point, you've been calling this a CPS semantics, but you're also pointing out, well, it can be implemented as a big step interpreter.
Right.
In a sense, it is an abstract machine as well, but I suppose those two are just very closely related.
Right. I think I didn't call it as an abstract machine because it's used those continuations just as functions in the meta language. If we defunctionalize those continuations to be some first order struct, I think that's more closely to like an abstract machine, like a CEK machine.
Yeah, no, exactly.
Yeah.
But I mean, morally, they're more or less the same thing.
Right, right.
Yeah, the question I have for you is, I like the idea of connecting this up with the small step semantics and using Olivier Donvie's work to radically extending that in order to support this. Supposing you have this nice relationship between the small step semantics and the CPS semantics, what do you think we should be using as the actual specification for Wasm? I mean, forget about all political considerations. If we just wanted the most ergonomic way of specifying it, do you think we should be using something closer to your CPS semantics?
So I guess one thing I originally want to do is to build a partial evaluator for WebAssembly, like using Scala, those staging techniques. I think CPS semantics would make things much easier compared to the official reduction semantics. And one thing is those the introduce those administrative instructions as a semantic specification breaks the binding times because the source program is supposed to be static, but some of the instructions somehow becomes dynamic in terms of their binding time because they're introduced on the fly while running the program. So that seems a bit tricky to work with, which is actually the original motivation I look at this. So I guess generally, I hope it would be useful to specify program transformation in the style of big step or slash CPS style.